Okay. So welcome everybody. So today we are going to start looking at specific inference algorithms for solving fairly specific problems, namely, for instance, clustering. That's going to be useful to understand at least the most basic of inference strategies. I mean, we'll dive into this a little bit deeper also in the homework, and my guess is we'll do a little bit more of that also again. Whoa. Right. Now the color should be okay. We'll do a bit more of that then also in the recitations again. Okay. So after that, we'll have one lecture of recommender systems, which I think it's important, and then probably the rest of the class will be all deep networks. And we'll probably skip a lot of theory. Okay. So are there any questions from last week? So basically, all that junction tree, message passing, that was all fairly abstract. Did the recitation help at least a little bit? Any questions? No questions? That means everything is either super clear or you're so confused that you don't want to ask questions. I hope it's the former than the latter. Okay, fine. Let's look at clustering. So basically, everybody's heard of clustering. It's like, well, you have all this data, and you can assume that there are subgroups of the data. And then within each of the subgroups of the data, well, yeah, that data has more in common. And so a good way of describing the data is by saying, well, there are certain groups. So for instance, if I were to cluster the people here in this lecture theater, I'd probably say there's a group on the right, there's a group on the left, and then there's this single guy standing out here who's an outlier. Right? How would we model this? One way is through something like this. So this is the simplest way of doing density estimation. As a matter of fact, we've already done this. Right? This is not clustering yet. So the assumption there is you have this one parameter theta. Let's say, for instance, mean and variance of a normal distribution. Or, this is like your reference language model, or, maybe Poisson counts. And then you should simply draw instances of that. And you assume that the data is independent of each other, conditioned on theta. So x given theta is conditionally independent. That's a very, very useful model, and we've done a lot of that before. So for instance, all of our exponential families models effectively assume this. Mind you, this is actually something where the joint distribution over theta and the x's is exchangeable, not independent. Exchangeable because the order in which I see the x's clearly doesn't matter. However, it is also clear that the x's are not independent of each other. So for instance, if I again the example of the socket of the wall, if I show you a couple of voltages like 110, 110, and 0 volts, you can pretty much infer what the other voltages should be, so they are clearly not independent. However, conditioned on the voltage that comes out of the outlet, the measurements are independent. Right. Okay. The problem is, well, what if it doesn't fit? Yes?
When you say draw latent parameter theta, do you mean that's how the world is working? The world draws a latent parameter, or that's what you actually do when you model something?
Okay. Very good question. I can only give you a philosophical answer. So first of all, what you'd really have to do is to have some prior alpha, and you would assume that this holds. And then you assume that alpha is observed, and alpha is the hyperprior. It's the hyperparameter. Then you could say, well, how do we know that alpha is really, that this relation is how the world works? Well, no, of course we don't. So we could have some beta. And then you could ask, well, is this really how the world works? And we could have some gamma. And at some point you run out of space. But the point is, okay, this sounds like a joke, but it's actually how people do it. So by adding hierarchy to your priors, you're making it a little bit easier to automatically adjust how the parameter should be set rather than just setting the prior. So for instance, if I know that my data is drawn from a normal distribution, it would be quite foolhardy to assume that it's zero mean and unit variance. A much smarter thing would be to assume that we have a conjugate Gauss-Wishart prior, and that now we draw the mean and variance conditioned on this Gauss-Wishart prior. Right? So this way I'm allowing the data to actually help infer the right parameters. And as I observe enough data, then eventually that will all work out fine, but only, of course, if I have a normal distribution. Okay. Now to the philosophical part of your question, namely, how do we know that this is how the world works? I forgot exactly which famous statistician I said that. I think it was Fisher, who basically said that all models are wrong, but some are useful. And I think that's pretty much how you should actually view a lot of the statistical modeling. So in other words, do not assume that just because your model actually so happens to fit the data reasonably well, that your model is the truth. It might be a reasonably good approximation of the truth, but it is not the truth. Right? So here's a simple example that we all know. So Newtonian mechanics is something that is an extremely useful model, right? So that's basically how people engineer cars. That's how the seats are built. That's, how you usually behave, and everything is fine. Now we all know that this is not the truth. At least we know that there's a better model, namely, special relativity or then general relativity. Now, do you care about general relativity on your way to university or not? Probably not, because even if you're late, you're never going to reach that speed, right? So what this means is that even though the model is clearly wrong in the mathematical sense, Newtonian mechanics, it is an amazingly good approximation, and so I can actually use it to reason about things, right? So this is something that you should keep in mind. Also, for instance, when people tell you, well, they have L1 sparsity estimators with certain oracle properties and all that, if you read the fine print of the theorem, it pretty much goes like, something wonderful happens, footnote, if the assumptions of the theorem are true, and the assumptions are usually that the model actually happens to be sparse with certain parameters. There are a number of results that are a little bit more general, which go like, well, under any assumptions, this model will do well, even if the modeling assumptions aren't exactly true. Those are much, much stronger statements, and they are much harder to prove. So in other words, read the fine print on your theorem before you claim that you found the answer. And trust me, I've seen people who are very senior and, way more senior than me, who fall into this trap over and over. Don't fall in love with your model, statistical model. Okay. Now, here's one of the problems that we get with, this, single density estimate. Well, if you think about the exponential families, well, this is, very nice. I have a normal distribution, I have a Poisson, I have a binary, I have stuff. Okay. And so you could ask, well, does this let me describe reality? And of course not, because data is a lot more interesting than those 10 things from the exponential family where somebody managed to solve the integral. And that's really the definition of what is in the exponential family. If somebody managed to solve the integral, and if it's interesting enough, then it's probably in there. Otherwise, it doesn't have a name. Okay. So now, since reality happens to be a lot richer than this, we need to actually use, for instance, members of the exponential family or other distributions as building blocks to construct more flexible, richer models. We already did that to some extent when we used kernel density estimation, right? So there we basically effectively put a Gaussian or an Eperneshkov or whatever around each single observation. Now, effectively what we're going to do here is we're not going to go quite so crazy to have so to say, one model per data point, but we're going to have a bunch of models. Maybe 10, maybe 100, maybe 1,000, maybe 10,000, right? But, not many millions. Okay. So in this specific case, what I'm assuming is that we have a couple of maybe Gaussians with some mean and covariance, right? And I'm going to use these in conjunction with some y's, which basically essentially allow me to switch between those different means and covariances to generate the data x. So in a way, what I do is I first generate my means and covariances in one bucket. Then I go and let's say I want to generate 100,000 observations. I generate 100,000 integers going from 1 to some smallish number. Then for each of those numbers, I draw the corresponding normal distribution out of my bucket, and I draw from it. Right? So this is mixture of Gaussians. Since it's really awkward to draw this thing, it takes way too much time. Statisticians, of course, have come up with a lazier way of doing that. And there you go. It's basically the same thing in plate notation. Trust me, it takes a lot less time to draw this. And what's happening here is, okay, we have our Gaussians. Here we have the yi's and the xi's. It actually also, makes the structure a lot more readable. Okay. And so, of course, what you need is hyperparameters, alphas and betas, and they control everything. So, and then, of course, we can go and, write out the joint distribution. By the way, the slides are up, so you can just download the slides if you want, but I'm not that photogenic. So basically, P of x and y. So all I'm doing is I'm just reading off really what this directed acyclic graph does. So I'm assuming that I have the P of yi's given theta, product over all the yi's, because they're all children of theta. I have, oops, I screwed up somewhere. Because, well, actually not really, because I conditioned on sigma mu. But if I were to look at that too, I would have to multiply here with, P of mu I sigma I given beta. And then, in the end, I have P of xi given yi sigma mu. Right? So the obvious question is, well, is this actually useful? And yeah. So here are things that have been clustered by people in industry. I think I ended up clustering at least half of those things at some point. So with emails, well, that's quite easy because depending on how you cluster it, for instance, if you think about your priority inbox and other things, you would basically group things, in this case, into important and maybe spam and maybe, okay, here's another special offer, basically some advertising spam and whatever. Text, well, I mean, you don't really want to find an article about Obama in the 49ers section, right? Where they maybe write about sports. Well, maybe you do, but it's quite rare. So products, likewise, if you're shopping for an SD card, you don't want to find a graphics card in there. Users, obviously, locations. So maybe you would have a cluster here at CMU. You might actually have subclusters because people congregate in buildings mostly. Events, ads, basically anything you can think of. Clustering is not a bad way of actually making this data representable and interpretable by humans and also readable otherwise. Okay. So simple thing you can do then is a mixture of Gaussians. So you go and, well, as I said, you draw the cluster ID, and, well, we're actually going to do a little bit of that in the homework. So what you could do is for discrete distribution, you have a Dirichlet. For Gaussians, you have Gauss-Wishart. Now, here's a problem. So if we actually knew those parameters, those means and variances, and then it would be very easy to infer what y should be. You could do this in a maximum likelihood sense, or you could just compute p of y given everything else. So this will give you the probability that an observation is in a cluster. Likewise, if we knew all those cluster memberships, we could really easily figure out what the parameters are. A quick warning / public service announcement here, because I've seen it done wrongly many times over. When you do clustering, and sometimes people refer to this as soft clustering because, well, you basically can ask, what's the probability that a particular observation belongs to a particular cluster? Well, that doesn't mean that therefore an observation belongs to more than one cluster. It still only belongs to one. So let's look at a specific case. Let's say you're really far away from a traffic light, and so you can't quite see whether it's really red, green, or yellow. And so even though the light can be in one of three states corresponding to three clusters, maybe your estimate of the probability P of green given the traffic light isn't going to be exactly 1, but maybe it's only 0.9. Right? So that doesn't mean that the traffic light at the same time might be displaying red, green, and yellow. It just means that you're not quite sure. Right? Or rather, that the sensory impression that arrives at your eyes could have been generated by any one of those three states. Right? That does not mean that you have a multiple cluster membership or that what you're observing is a mixture of those clusters. It just means that you're not sure. Okay. I know this sounds painfully obvious, and I probably had at least 20 discussions of that very form with engineers who misguidedly thought that this tells you, therefore, the mixed membership for an observation. There are other models which will take care of exactly that. We will probably not have a lot of time to go into it, but if you're interested, you should be looking for something called topic models. Okay, good. This is not topic modeling. Yes?
Two questions. One is that PCA is a form of clustering, right?
Thanks. Thanks for asking. So PCA is much closer to a topic model. So in PCA, if I, let's say, take your photo and I decompose it into the eigenfaces, then none of those eigenfaces will look particularly human, nor will any of those look particularly very much like you. However, if I compose it and look at the leading terms, then it will look like you. So if I were to cluster, then what I would do is I would take pictures of everyone, and then I would maybe infer that you look like some person over there. Or at least you would visually belong to a similar cluster. Maybe I would put everybody who, wears glasses into one cluster, and then maybe I will cluster by hairstyle and whatever. Or maybe then by shirt color, right? So the point being, PCA is very much an example of this factorial representation. The difference between topic models and PCA in a way is that topic models will give you a rather much more sparse representation where you only take a small subset of dimensions as opposed to everything. Right? So thanks for that question. Second question.
In that case, the projection onto the eigenspaces is actually a mix.
Correct. Yes. So that's the converse conclusion from that. That then, yes, those various projections onto the subspaces actually mean something. Namely, they are going to give you the extent to which you look like, direction number 1, direction number 2, and so on. Right. So that's, yeah. So very good question. Okay. Other questions? Yes?
Factorial representation.
Okay, what does factorial representation mean? Okay, So that basically means that there are a couple of factors that actually represent an observation. So let's talk about user profiles, right? So, for instance, one of the attributes might be gender, another one might be age, another one might be whether you're a nerd. Maybe some of those slightly correlate with each other. Maybe one aspect would be, whether you're a Mac user or a Linux user or, God forbid, a Windows user, right? And it goes on like this. So that will give you a mixture of attributes. And while they certainly may correlate, I think there's a stronger correlation between you being a nerd and you being a Linux user, right? So these attributes may not completely occur independently, and then you can actually go in a secondary stage, model this in a higher level up. Now, usually, life doesn't give you those factors directly because it's amazingly intrusive if you go to a website and it throws these horrible queries at you. Well, what is your household income? How old are you? By the way, how many people are there? And so on and so on. And this is, in a way, trying to elicit some very crappy way of a factorial representation, right? So what you often get is you just get the observations arising from this. And then you need to backwards infer how those things work. So for instance, if you look at Quantcast, this is a website that tries to infer basically, who the audience on the website is. So I've got their tracker running on my website, and you can go there and check what Quantcast thinks that the typical users of my site are. And while it shouldn't be shockingly surprising that essentially, well, let's just say a typical user of my website is in their 20s or maybe early 30s, often male, and often from Asia. Duh, yeah, sure. Look around and you know why. Okay, so that's what you can sometimes do, and some of those models are better than others. Quantcast is, I hope they improve their algorithms. Okay, but it's useful in debugging information. Okay. Yep. So here's a really simple way how you can get those clusters. And that's k-means. And my guess is about half of you would have heard of k-means at some point in your life. Who has heard of k-means so far? Yay! That's cool. So k-means is sort of the stupid bastard child of basically mixtures of Gaussians. Basically what we do is we fix a uniform variance for all the Gaussians, right? This is about as horrible as it gets. It's really wrong. And we also assume that each cluster is equally likely. So I'm not even going to learn that. So then, next thing you do is you basically initially assign all centers with random subsets of points. Okay? So they all look pretty much the same, just a little bit off. And then you go and find the most likely cluster Y, for X. So once you infer what your means are, you basically reassign the data to those clusters. And then you go and just find the most likely cluster center for the given cluster. So this is a very, very simple algorithm, and it's very, very easy to parallelize, at least in a stupid way, and at least if you don't have too many means. Because what you simply do is, let's say I have a lot of machines, I go and send each machine all my means. It independently goes through and computes the points assigned to those means, computes the corresponding updated center weights. Then I aggregate all of this, update the means, and send them back out. And so one of the earlier algorithms which then, quote, proved that Hadoop was wonderful for big data was to simply run k-means in a distributed fashion. There's a lot of things wrong with this, but it's the first algorithm, and people use it quite a bit, and it's probably still in use. And k-means is often not a bad initialization for other smarter algorithms that follow afterwards, not to the least because it's such a simple algorithm. Any questions? Okay. Well, the obvious pro is that it proves simple that I think everybody would have heard about that probably in the first or second year of university. And the con is, well, it's just a really crummy statistical model, and it can get easily stuck in local minima and so on. So, well, you use it as a baseline. And yeah, okay, so, you initialize, you pick a couple of cluster centers, you partition the data, and then you update, and you keep on doing this over and over, right? So that's how k-means works. Any questions about k-means? Because it's so stupid simple that, you really don't need to go through it a lot. Yep?
Partitioning is based on the nearest...
Sorry, I couldn't catch the first part. Can you repeat that?
Yes. Partitioning is based on finding the nearest point.
Sorry, what was the first word? I just got... Partitioning. Oh. Well, yeah, well, it's... Well, if you assume constant variance, if you assume fixed variance, and if you assume a uniform prior over all the cluster centers, then yes, this would be the most likely assignment of a point to a cluster center. Yes. So yeah, to that extent, it's still somewhat theoretically motivated, but since it already violates so many other things, I would simply consider it a heuristic. So one thing that you could look at is k-means attempts to minimize the least mean squares distortion error between the data and the points. Right. So for instance, if I had photographs and I really wanted to minimize the least mean squares error in compressing those photographs, then k-means might not be such a horrible thing because I would actually try to minimize the least mean squares fit. Okay. So, yep.
But if you don't know number of classes, how can you use k-means?
Okay. Okay, you got me with that one. So first of all, in k-means, what people usually do is they just take some number that they think is good, right? So for instance, if you're doing computational advertising and your system can only process maybe 10,000 clusters, then that's what you're going to pick. Is 10,000 the truth? No, of course not. Okay. What also happens is in k-means is you will run clustering for a few steps, and then you will look at all the clusters that aren't really doing anything useful right now because they hardly get any points assigned. You throw them out and you place them in random new locations. And you keep on doing that until at some point, well, you're kind of happy with the outcome. Okay. Slightly more principled version is there is actually something called Dirichlet processes, and this has a lot to do with Bayesian nonparametrics. There's an algorithm called dp means. So Brian Coulis. I think he's in Ohio, some other cool place. So he did a lot of that during his PhD and then postdoc. You might want to look up his work. So basically, he looked at various algorithms for looking at k-means, turning it into Dirichlet process means, and also looking at hierarchical versions of this. The entire motivation of that, however, is Bayesian nonparametrics, and it's probably a good idea to look at just Dirichlet process clustering before that. It's a wonderful area. Not enough time to go into this here, but let me just quickly give you the high-level idea. What you do is you basically construct a distribution over the number of cluster centers. Or rather, what you do is you look at the distribution over partitionings of sets. That's really what happens. And so, therefore, the number of clusters effectively is just, the number of distinct partitions. And so you can then start thinking about, well, how do I go and design such partitions? And one way is, for instance, by essentially preferential attachment. There's something called the Chinese restaurant process. And since the title is so cute, I can quickly give you the intuition. So if somebody tells you they are doing CRPs, it's nothing particularly fancy. But here's what happens. Assume you have a gigantic Chinese restaurant with an infinite number of tables. And the first customer walks in, and okay, sits down at the table. The second customer walks in. He looks around and can either, pick the same table as the previous guy or pick a new table. And since we have an infinite number of tables, we'll never run out of tables. And what happens is that the propensity of picking a table that already has people on it is going to be proportional to the number of people sitting at that table. So basically what happens is that you will have propensities proportional to nk, the number of people sitting at that table, and you will have some alpha which tells you, which is basically the attraction of a new table. So basically alpha is people equivalence. So if alpha equals 2, and I have 3 people already in the room, then chances of picking a new table are going to be what? Tell me. So somebody should be able to tell me that probability. I have 3 people in the room, alpha equals 2. What's the chance of picking a new table? 2/5, exactly. Correct. And that is actually what you would also get from a Dirichlet process prior. So the Dirichlet distribution, remember it used counts, and this is basically using counts over an infinite alphabet. Okay. And you can actually derive this in a limit distribution. And if you like these things, you really should take, I think it's 10705 or 10 something higher. Basically, you should take the graphical models and Bayesian methods class. There's a lot of wonderful things you can do there, not enough time to cover in 701. Okay. So I have plenty of slides and other lectures online that where you can look at that kind of stuff up. Scaling this up is not entirely trivial. Okay. Now let's look at the more simple overview of how to do inference. So, after all, we could just say, well, hey, we learned about message passing, and let's just do it, right? So we can write out, the directed graphical model. And the first problem is that we cannot generate a thin junction tree. Right? And that has a lot to do with our cliques being a little bit malformed here. So this will couple all of the stuff together. So therefore, we cannot do exact inference. So life is easy if you can do exact inference, but, we can't, so we need to actually hack it quite a bit. And that's what we're going to do. The problem is that variables like this one here will lead to huge messages. Because what you're basically now doing is you're telling this guy how much it is interacting with the rest of the world, right? Like with this one here. And expressing this explicitly will lead to a massively multivariate distribution with all sorts of properties in it, so it's not fun. So people have resorted to approximations. So one thing you could do is you could just ignore the fact that you have a junction tree, and you just send messages between the vertices, and that's still really expensive for high degree vertices. So in other words, you still have a problem with these guys here. But then what you can do is you can maybe say, maybe I don't have to really send the correct message, but I can just approximate that. And this leads to something called EP, expectation propagation. So the guy's name to look up in this context is Tom Minka. And he has written fairly extensively on that work. Okay. Yeah. So if you want to do explicit message passing and you want to make your messages cheaper, or if you are from Microsoft Cambridge, then you will use EP. So basically, if you want to learn about it, you should do an internship there. It's cool stuff. Okay. What you could also do is you could say, well, okay, I don't actually care about the truth. I just want to maybe find the mode of the distribution. And this is easy, and it's often quite wrong. So if you look at it, you can see that actually, for instance here, it will pick this term here as a mode, but that's actually much closer to the mean because this is maybe not such a, has so high density, but it has a lot of probability mass there. And it will get stuck in local minima, and you will have very little recourse to find out exactly where you are. But people use it, and k-means is quite commonly in use. So, well, now let's look at slightly more costly algorithms. One is to use sampling, and one is to use variational inference. Okay. So sampling is actually a very, very simple idea if you think about it. Well, maybe I don't really have access to the full probability distribution, but what I could do is I could just go and draw from one observation, from one random variable after the other. So I could basically go through it and, let's say, draw from y1 given the rest, then y2 given the rest, and y3 given the rest, up to ym. And then, lo and behold, I can actually now go and, for instance, draw from theta. As a matter of fact, I could have drawn from all the red guys at once. And furthermore, given the y's, I can also draw from the mu's and sigmas. So you now get an algorithm that alternates between drawing from the red set of variables, namely the y's, and the blue sets of variables, namely the thetas, mu's, sigmas, and all that. Because basically, if I know the y's, the data decomposes neatly into subgroups. And for each cluster, it's just fitting a Gaussian. So it's just drawing from the posterior of a Gauss-Wishart, and we all know how to do that. And furthermore, given the y's, it's just drawing from a, Dirichlet multinomial here in order to draw the theta. Multinomial because that's exactly that distribution, Dirichlet because it's its conjugate. And if you don't recall how to do this, you go to Wikipedia and you look up the cookbook recipes. Wikipedia is pretty amazing at that. So it's not a big deal. Okay. So this actually works reasonably well. What this will give you is a sample drawn from that distribution. And the specific sample that we're looking at here is something called a Gibbs sampler. There are a lot more fancier algorithms than just Gibbs samplers, but Gibbs samplers is pretty much as we'll be able to get here. There's something called Markov chain Monte Carlo. So again, consult a more advanced machine learning class, or consult Wikipedia, or, well, read a paper. It's quite a bit beyond the scope of this here, but you will need this if drawing from each of those yi's individually is expensive and, a few things like that. Yes?
So is the Gibbs sampler kind of like a hierarchical parametric bootstrap?
I don't see how those two would be very much related. So, okay, the Gibbs sampler will after you run it for long enough, so don't expect to just draw one set of y's and then one set of mu's and thetas to give you something sensible. You might want to run it between 100 or 1,000 iterations, right? Which actually can make this entire thing very costly. And what you will get then is a single sample from how the y's and mu's and thetas could be. Now, if you actually want to do something else and useful with this, you might have to run it, maybe another 100 steps, then read off the next sample, and you keep on doing this for maybe 10, 15 times, depending on how many samples you want to get. Yes?
It says iterate until converged. What does convergence mean here?
Okay, so what I mean by convergence is initially my initializations of the mu's and y's and thetas will be bad. They're probably going to be totally wrong and not really representative of the data or anything. What I want to do is I want to run it until I actually have a proper sample drawn from the distribution that I want to sample from. So basically, I start out with some sample from a distribution that's quite wrong. And by iterating the sampler for long enough, my distribution over choices will converge very quickly to the true distribution. The speed at which it converges to it has a lot to do with eigenvalues of Markov of transition matrices and so on, but that's, again, way beyond the scope of this here. Rule of thumb is between 100 and 1,000 times. Now, you would probably notice that if I did this for clustering long enough, I would get garbage. I would get garbage insofar as, for, just k clusters, there is no particular reason why, let's say, the first observation should be in cluster number 5. There's no reason whatsoever. Instead, observation 1 could be in any cluster. Or rather, that the cluster that I call cluster number 5 should be, should really have the index 5. It might at some point be called 10, at some point be called 20. So what, however, is going to be meaningful is to ask the question, what are the chances that observation 1 and observations 2 are in the same cluster? Right? So the numerical cluster ID is quite meaningless, but the actual co-membership in clusters will help you. Nonetheless, what people usually do is they will run it, and then they draw a single sample, and it will give you not a bad estimate. The reason being that you usually get concentration of measure, as in decent estimates, in the means, and in this term here. Yes?
When you said in the first slide that Bayesian inference is impossible, you meant it's theoretically impossible?
Well, it's computationally hopeless. Yeah. So this is Bayesian inference here, right? It's just that you will not be able to solve the integrals analytically exactly. So it's just like, for most functions, integration is impossible in the sense that I will not be able to give you the exact value of that integral. However, I can happily point you at 50 different libraries which will approximately solve the integral for you. And so it's only possible up to some imprecision. Good catch. Okay, good. So then let's look at something else that we could do. And there's something called variational inference, and this will lead to what's called the EM algorithm for clustering. Now, most of you would know the EM algorithm in the context of clustering, but I want to really, really make sure this sinks in. Variational inference, aka the expectation maximization algorithm, and clustering are two different things. Think of the EM algorithm as the driver and clustering as the car. Right? You can use variational inference, aka EM, to infer a lot of other things. You could use it for Markov models. You could use it for, topic models. You could use it for anything. Likewise, you can use a lot of different algorithms for clustering. such as sampling, right? It's just that it's usually explained together because, first of all, that was one of the first occurrences in the literature. Secondly, because it's most easily explainable this way. But I hope that nobody in the end will say, well, we use EM, so therefore we use clustering. Because no. And often people aren't particularly religious about any specific aspect of those inference techniques, and they may actually go and combine pieces. So they might combine a maximization approach in one part with a sampler in another part, with maybe message passing in the third part. And those design choices are often based on what your data is and what your computational ability is. And sometimes just how hard the math is. Okay. So the idea in variational inference is very simple. Rather than picking the true distribution of, P of y given the rest and, P of mu and sigma given the rest, you pick a simple distribution. And in this case, we're going to pick something that factorizes. So we are going to approximate this by essentially this guy here and these guys here. Right? So what this means is we will have a lot of independent random variables here, q of yi, mu I and sigma I, this one here. And we will have, one simple factorial model, q of y given theta. So I could have done something different. I could have, for instance, picked a different, factor for each of those terms here and made it all independent. But the more structure of the original problem that I can preserve, the better. So in other words, what you do in variational inference is you look at the problem, you say, well, how much of the structure can I salvage? How much can I keep where, exact inference within that structure is still possible? And then you try and solve the problem within that structure. Okay, so let's make it a little bit more concrete. And yeah, that's basically what happens. Okay, so now let's take a step back and let's just think a little bit about optimization problems. And the connection between that and what we had before will become clear in a moment. So let's say I have some non-convex optimization problem, like in this case maybe maximize over theta, mu, and sigma, p of all the data given those parameters. Right? And that's, of course, hopeless, so can't really solve it. But maybe we can decompose it. And here's the entire picture that you need to remember about the, EM algorithm. This has been invented and reinvented at least 3 or 4 times in literature, and there are entire schools of papers describing the same algorithm but with a different name. One school is called expectation maximization. The next one is called DC programming, as in difference of convex functions programming. The third one is called the M method. They all do exactly the same thing. They just have developed their own terminology, and since this happened, at a time pre-internet, basically 3 different Galapagos Islands blossomed, and yeah, people still continue this because they have too much invested. But so here's what really happens. Let's say I have some function f, and it's just any run-of-the-mill function. I can write it into maybe a convex plus a concave part. Right? I can always do that. Well, one way, for instance, of doing this is, let's say if it's twice differentiable, I look at the second derivative and decompose it into a positive and a negative part. I integrate both by parts up to the second stem function again, and voila, you basically have the original function properly decomposed. In most cases, you won't have to do anything as fancy as that. You'll just squint at the function and you'll see exactly what happens. Right? So usually there's some very nice lucky guess by which you can decompose a general non-convex function into a convex and a concave part. Now, we know by Taylor approximation, so that's about as complicated as it'll get, namely not very much, that the concave function is, of course, bounded by its first order Taylor approximation. So, in other words, I have this. Okay, maybe I shouldn't draw blue on blue. Okay, so this is my concave function. And I can now go and just put the tangent on it. And that's an upper bound, right? So therefore, what I can do is I can take the convex function plus the linear upper bound on the concave part and minimize that. Because we know how to minimize convex functions, so this is easy. Okay, so I've just minimized an upper bound. On top of that, I've minimized an upper bound that was tight at the point where I started, because at the origin of the Taylor expansion, the upper bound is exact, right? Basically, at that point here, the Taylor approximation is exact. So I minimize an upper bound, I win. Then I go, and at the new location that I've computed, I recompute my upper bound. Again, I win because I tighten the gap again. I make the gap 0 again because I'm computing new Taylor approximation. And then I go and solve it again. So DC programming, difference of convex functions programming, which is exactly what we have here, you know, convex plus concave, or convex minus convex, if you will. That's exactly what happens here. Okay. And here's an example of what you could do. Maybe you start out here, right, this function, and you get the Taylor approximation, so maybe you get that as the next solution, and you keep on doing this. And at some point, you will find a local optimum. You're not guaranteed to find the global optimum, but you will find a local one. Okay. Any questions about DC programming so far? Yes?
Just in that picture, so would the global optima be the other value?
Yes, because that's lower. Well, it could be that far over here there's something else that's even lower, and I wouldn't know it. But this is clearly not the global optimum. And I drew it in this way just to make it, painfully obvious that while you will get the local optimum, you have no global guarantees. Yes?
This looks like terribly like Newton's method.
Well, it's not exactly Newton's method, because in Newton's method you would actually perform a quadratic approximation of the convex part and then solve that. You may very well go and actually invoke Newton's method to solve each of those subproblems, right? But this may not be the best use of your computation. Probably a conjugate gradient solver is good enough, because you don't necessarily need to solve each of those subproblems to optimality. You just need to solve them well enough that it's worthwhile computing a new tangent, right? So, in other words, it's perfectly okay to be sloppy at each of those steps and just get better and, more careful and meticulous towards the end. Yes?
So the problem is, it's not about using Newton, but the problem is the convergence. Will it always converge to a local minimum?
Will it always converge? Well, that's a little bit harder, because you can get cases where maybe the problem is unbounded, and that then depends also to some extent on your second order procedure. There are results on the convergence and convergence rates that are a little bit trickier, but so look, for instance, in the original Dempster-Laird and Rubin paper, they do give some analysis of the convergence rates for the EM algorithm. So since this is quite a bit beyond the scope of this class, I recommend that you look up that paper if you want to find out about convergence rates. I don't know exactly how many citations this paper has gotten. If you just type those 3 names in, you'll find it. My guess is it's probably between 10 and 100,000. It's one of the most cited papers in statistics. Yeah. And the C programming, that's by some group of Vietnamese mathematicians in France. And they were a little bit earlier, I think. Just a couple of years. Of course, if you read the Dempsey-Laird and Rubin paper, it will not be clear that this is what they're doing. But that's really the algebra behind it, and I want to make sure you recall that technique, because you'll encounter that problem quite often also otherwise. Just if you have a general non-convex problem, what are you going to do? Okay, now let's actually use this for a very specific case, namely EM. And so now we'll have to do a little bit of math. I'm sorry. There's nothing you can do about it. And okay, let's just go through it in detail. So I guess everybody by now would have heard about the Kullback-Leibler divergence, because we did this actually in recitation. That's why I asked the guys in recitation to cover information theory. That's the only reason why. So if I have log of p of x parameterized by theta, I can upper bound this as the log of p of x parameterized by theta minus the KL divergence, right? I can do that. So therefore, this gives me a lower bound on p of x parameterized by theta. Right? I can just add anything, I can just subtract anything no negative from it, and it's going to give me a lower bound. That's step 1. Okay. And in particular, I'm going to look at the KL divergence between Q of y, which is what's going to be my variational distribution Q, and P of y given x and theta, which is, and the y's are just some auxiliary variables. Like in clustering, they might be the cluster memberships and also the means and variances. X is my real data. So in other words, rather than instead of maximizing p of x parameterized by theta, I go and maximize the lower bound and I make progress, then I'm still doing something useful. Right? And furthermore, I know that if I pick Q of y equals p of y given x and theta, then this is going to be 0. Okay. So now let's actually write out the KL divergence. The first thing that I can do is, so this is an integral over Q of y, I can pull the first term into the integral. That's the case because this doesn't actually even depend on y. If I have an integral that integrates out to 1, then 1 times something is still the same term. Right? Now, I also expand the actual KL divergence, which is this term here. And now something very nice happens, namely, those two terms together are going to give me p of x and y parameterized by theta. And furthermore, I have a separate term here, which is, well, dq of y log q of y. Okay. Does somebody know what that second term is? Okay, anybody? Yep. Exactly, this is the entropy. And the first term is basically the expected log likelihood of the model p of x and y parameterized by theta under that assumption that the y's are drawn from Q. So basically the first term is essentially how well our parameters explain the missing parameters y and the data itself under the assumption that Q of y is the truth, and I also penalize it by the entropy. So in other words, I want to have a as uncommittal version of Q as possible. That's why I maximize the entropy by maximizing this term. Because this thing here is, including the minus sign, is H of Q. And then you can go and, so the nice thing is that this actually decomposes now. So I can now go and optimize over the first term, this one here, separately. And then I go and pick another Q again. And then I go and optimize over this again, and I pick that again. Okay. So what have we done here is we have actually just designed a variational method. What you don't see yet is that this is actually a Taylor approximation. So basically, what will actually happen is that this Q of y is effectively the gradient. We'll get to that. Okay, yes, you should pick this. And so you go and find a bound, and of course, this bound is only tight when I have P of y given x equals Q of y. And then I just perform a maximization step in which I go and maximize with regard to theta the first term. This is EM in one slide. Quite often you will see this derived in a much more general form for, well, a much more specific form for a very specific expression of P of x parameterized by theta. And then you end up with about 1 page of math, and magically in the end it all works out. But this is the 3-liner proof to rule them all, right? So remember this one, then everything else is easy. It's basically just subtract the KL divergence, and then everything else is just mechanics, right? If you will, this is the key step. Everything else is trivial. Right. So, does anybody have questions about the concept of the EM algorithm? Yes?
In the expectations that shouldn't that be the probability of y given x and theta star? Like the last theta that you
Yeah, yes. Yeah, I mean, we need to instantiate theta.
Sure.
Yes, that's what happens. Yeah, we need to plug in a value of x, we need to plug in a value of theta, otherwise we can't have a Q. And I was playing fast and loose with indices here, not to, and maybe that confused more than it clarified things. Yes. Good catch. Yes?
This is done iteratively, right?
That's what?
It's done iteratively.
Exactly. Yes.
And then, so the convergence guarantee here comes from what's that?
Okay, so for some specific cases, Dempsey-Laird and Rubin actually work out some indication of what the rate might be. And, well, I'm saying some indication of what the rate might be because it will depend a lot on the data that they're dealing with. So they don't really have so strong rates a priori anyway. In many cases, you run like 10 or 20 iterations. I know that's not very satisfactory, but this will typically work reasonably well. And the good thing is you actually have a convergence monitor to some extent, right? Because you can always evaluate this bound here, right? You can always directly calculate what comes out of this here, or rather of this quantity here. And so you just plot those numbers, and you see at some point when you're done. Yeah. And then usually the argument goes, well, since it's a since it's a non-convex problem anyway, well, we don't really have much of a handle, and you just, throw your hands in the air. No, that's not what you wanted to hear, but yeah. There are other algorithms that are maybe slightly less stupid for non-convex optimization, such as BFGS. And people have sometimes used BFGS as an alternative or as a subroutine to some parts of EM. Or sometimes people will combine that with stochastic gradient descent. So this is sometimes then called stochastic EM, where you keep on updating your model all the time. Sometimes they design what's called stochastic variational algorithms. They're actually really, really cool things. So Matt Hoffman has been doing a lot of really good work on that lately, basically over the past 3-4 years. So there's a lot of really fancy innovation that's happening right now in this area, but that would require rather a bit more math. But so talk to me afterwards and I can point you to the paper if you want. Okay. So let's actually make that a little bit more practical. Let's look at EM for clustering. So the factorizing distribution in the y's, I can make it about as simple as it is. So I could have something like Q of y. It's just the product of Qi of y. So I'm not even modeling the joint parent anymore. I'm just modeling, Qi of y. Okay. And in that case, well, Qi of y, well, that's just, P of, in this case, P of yi given everything else. And, well, by Bayes' rule, we know that this is, P proportional to P of xi given y times P of y given theta. So we just need to renormalize. And this actually works out to be something rather pretty, right? Because this is essentially, this term here is how well the model fits. The blue bit is basically, what my prior probability would be that this particular model would be chosen. And so it's really the product of those two terms that I use to decide whether, a point would belong to a particular cluster. Okay. And so here we have our normal distribution. And here we have our prior probability, P of y. What you can see is that this is basically, what distortion error you're incurring. But it also means that if I make my covariance really, really wide, then, well, I have to pay here overall for it. So I can't just go and, pick a really, really wide catch-all cluster and hope that it'll soak up all the observations, because it will just be fairly poor throughout. Okay? And then I just need to renormalize, so I get these terms here. Okay. And then I use just standard maximization step. And here, I basically need to just compute the log likelihood, log P of x and theta, log P of x and y, given theta, mu, and sigma. So I get this. And then I just go and, optimize over the means and the variances. And likewise, I get the cluster probabilities. So this is really just standard Gaussian inference. You're actually going to go through that also in your homework to some extent. Yep?
You write summation over I of Q sub I of y. Is that the same as Q of y sub I, or is the y a dummy variable and you're assuming that the Q's might be different?
Okay. So I really should have written Qi of yi. Yes, that's correct. I was just being lazy here. Yes, good catch. And what you basically see is that you end up, for the means, weighing each observation based on how much, your variational distribution Q thinks that this observation belongs to cluster Y. And likewise, the same thing for the variances. So it gives you a very intuitive algorithm. You could probably hack it together without any of the math by just thinking how an algorithm should be. That may be a good way of motivating, and sometimes people motivate it this way, but it will not help you at all solving it if you have a slightly different problem it's much, much safer to actually start with the math and interpret the math afterwards. Because interpretations don't give you a proof. Okay, and okay, this is what EM clustering does. And then, of course, you get a huge problem, which is basically that the estimates may actually diverge quite a bit. So almost invariably, if you run the algorithm as it is, you will get, basically infinite variances and, clusters that don't exist anymore and stuff like that. And the obvious way to avoid that is by imposing a prior. And my prior is simply to say, well, the cluster should at least occur with a certain probability, and they should at least have a certain amount of variance. Okay, and that's that. So basically, all you do now is you're going to use your conjugate priors and treat them as if they were additional fake observations, and you just add them in when you aggregate your statistics. So in other words, you just add your fake counts to the counts that you get from EM. You add your fake means to the means that you get from EM. You add your fake variances to the variances, or actually fake second-order moments to the second-order moments that you get from EM. And this is now EM with a smoother, which is probably way more advanced than 80 to 90% of all EM implementations. Because most people who hack EM don't understand this stuff. But you can do it better. Because it's really trivial. It's basically those three red dots. One here, one there, and one there. If you do this, your EM algorithm will be infinitely much better. As in, it will not diverge, and the other ones might. Okay. Any questions so far? I know this is a fair amount of stuff. You will need to probably review that at home and go through the math. I'm almost certain that you will want to do that. Because if you don't, this will not last. Okay. Yes?
What is K in the last one?
Oh, that's just, okay. Well, good question. So K is the number of clusters. And so if I assume that I have like a pseudo count of n0 per cluster, then the total amount of pseudo counts is, pseudo count per cluster times number of clusters. I need to add this to the true counts. And ny is, well, exactly this term here, pseudo count plus, basically the blame that I get from EM. So I can still get small variances and all that, but it doesn't diverge quite that much. Yes?
Are priors always equivalent to regularization?
Okay. In a way, yes. So but the other way around doesn't always hold. Okay, so you can get some optimization problems in some form of regularization where it's very, very hard to turn this into a corresponding Bayesian procedure. So the typical corresponding Bayesian procedure is to just exponentiate everything, take the negative exponential of it and say, well, voila, my probability distribution. But if I have a constrained optimization problem where I have all sorts of peculiarities of, basically getting, things that should have otherwise measure 0, then this would be a very poor prior. So for instance, if you think about the soft margin loss, right, which is basically linear and then 0, that does not correspond to a terribly intelligent, conditional probability distribution, right? So that's why taking your optimization problem and, just taking the negative exponential is almost certainly going to give you a really weird Bayesian model. However, you can often use a prior and say, well, can I design a corresponding regularization out of it? Now, the particular regularization that I'm using here is a very, very easy to understand one. It's the conjugate priors. Remember, we did that in class, and we also had one homework on that. Conjugate priors essentially equate to fake data. And they are really, really easy to deal with in many of those cases where you go and compute sufficient statistics, so basically aggregates of your data, right? There are some other cases where it's not so easy to deal with, for instance, maybe classification or regression, but here when we are doing effectively density estimation, this is really nice. It's also a very natural way of specifying your priors because, after all, what you're doing is you're saying, well, I'm seeing data and I'm adding some data that I think I could have seen, right? So if adding data with zero mean and unit variance looks strange to you, it means simply your prior is probably not the one that you should be picking, and you should be picking something else. Okay. So I don't think there's time to go into sampling. There's a little bit of stuff, but not enough time for it right now. We'll do that on Wednesday. Do you mind stopping the video? So one thing that